Hello there. I have to give this extremely long. Okay. Long relative to the other presentations you would normally give in school. And it's based off of a script I wrote that was going to be a mini documentary for this channel about a year and a half ago. 2,400 word script turned into a presentation. All because I was lazy and didn't want to research other crap. So, yeah. I'm doing this to prevent myself from being extremely anxious and a terrible presenter tomorrow. So, yeah. Let's get into it. Okay, so I'm prepared. Let's get into it. So, the universe, beginning to end, by me, obviously. Come on, Microsoft. Okay. The age of the universe. Okay, I shouldn't be looking and reading off of it. Okay. So, NASA estimates that the universe is around 12 to 14 billion years old. However, other estimates from NASA show that it is 13.8 billion years old, and that is more widely used in articles and stuff. So I'm going with 13.8 billion years old. So the Milky Way actually formed 13.21 billion years ago. So about 600 million years after the Big Bang. And And the solar system formed in the Milky Way, obviously, 4.5 billion years ago. So that was quite a while back, in terms of a human lifetime, even a universe. There's that. Next slide. The Big Bang, part 1 of 8, I think. In the first moments of the universe, physics really didn't apply. It's called the Planck epoch. The Planck epoch. I think it's epoch. Am I being drunk? No. Okay. In the first moments of the universe, physics didn't really apply that well. No. In the first moments of the universe, and when I say moments, I mean 10 to the negative 43rd power seconds of the universe, the standard model of physics didn't apply, and that was called the Planck epoch. About 10 to the negative 36th power seconds into the universe, the standard model of physics actually started to take effect. Next slide. Okay, the inflationary epoch occurred 10 to the negative 32nd power seconds into the universe. This was a major step in the formation of the universe, and this step is currently kind of still happening today, but different name, kind of, I think. The moment this started, the universe actually expanded by a factor of 10 to the negative 26th power in a period of 10 to the negative 33rd power, and then to... Oh my god. Okay, let me restart that bit. The moment this started, the universe actually began expanding, but that was by a factor of 10 to the 26th power in a period of 10 to the negative 33rd power, through 10 to the negative 32 power, 32nd power, after the Big Bang, seconds after the Big Bang. Also, during this time, the universe cooled a crap ton, from 10 to the negative 27, from 10 to the 27th power to 10 to the 22nd power Kelvin. The inflationary epoch also needs a whole slide, by the way. Thought I should point that out, my bad joke. So, next is the quark epoch. This happened the quark epoch happened 10 to the negative 12 seconds after the Big Bang. Quarks are one. So here's a little explanation of what a quark is. It's a elementary particle. I was right. Okay. And they combine to make hadrons. However, that's kind of unimportant right now because hadrons couldn't form because the universe was too hot, as you could probably not guess, but still. So instead of this, quarks combined. Wait. Okay, sorry. I had to check the slide for a second. So, the universe was still way too hot for quarks to combine. So instead, colliding quarks formed quark-gluon plasma by colliding with gluons. And quarks are about 10 to the negative 15th meters wide. They're kind of like an ant if you compare them to the Earth, or as my even worse comparison on the screen, like an ant but way smaller than that. This is the first second after the Big Bang, and we're already 4 slides in. It's brilliant, isn't it? The Hadron epoch occurred from... Nope. Didn't do that right. I read too much. Okay. So, I need some water. I'm really going to have to hydrate before I give this presentation. The Hadron... Fuck. Okay. The Hadron epoch occurred... Okay, so... Next, we are finally 1 second after the Big Bang at the Hadron epoch. The Hadron epoch occurred from 10 to the negative 6th power seconds, I was right, to 1 second after the Big Bang. During this time, quarks began to collide, producing hadrons, and also caused the total destruction of antihadrons. That's according to Wikipedia and one other source. Don't tell my teacher. Next, Big Bang Part 5, neutrino decoupling. Neutrino decoupling took place during the first second of the universe. During this time, neutrinos stopped interacting with baryonic matter. Neutrinos are very small particles. They are also elementary particles that only interact with gravity and the weak subatomic force. Don't ask me what that is. That's just what the first article on Google said. So it's a force that's weak and acts on subatomic particles. So, yeah. Next slide. So now we are at the lepton epoch, and this lasted from the first second all the way to 10 seconds after the Big Bang. Leptons and antileptons were in thermal equilibrium. Leptons are subatomic particles that weakly interact with gravity, electromagnetism, and gravity. So, there's that. Part 7, the photon epoch. Okay. So now we get to my hopefully not miscalculated math. So the photon epoch started 10 seconds after the Big Bang and ended 10 to the 13th power, or a lot of seconds into the universe. A lot of seconds, or 3.67 years after the Big Bang, according to my math which was done very hastily on a calculator. And there was no checks on that. So, yeah. At this point, the universe was made out of plasma, nuclei, and electrons. Elections, apparently. And photons. Should probably fix that. The universe at this time was far too hot during most of this time period for electrons to bind to the nuclei. They did bind to the nuclei soon, sometime in that period. We're not entirely sure. But during most of it, it was too hot. Next slide. Think of a really bad okay, This stage really matters, but you won't get that bad joke / kind of pun until I've gone over the slide, I think. Unless you're like a genius. So, yeah. So, the Big Bang nucleosynthesis, or not so fancy terms, all matter was created stage, lasted from 10 seconds after the Big Bang to 10 to the third power seconds, or 10,000 seconds, / 2.78 hours after the Big Bang. All matter in the universe was created in less than 3 hours. Not sure how that's possible. I'm not sure if that's accurate, but I guess it is. I'd like to point out that heavier elements were not created at this point. Hydrogen, helium-4, small amounts of helium-3, and lithium-7 were created during this time. None of the heavier elements, not like bloody uranium, and that was way later in the universe. I'll get to that. Yeah. Big Bang Part 8. Guess what? Next slide. No Big Bang. Matter domination. So, this occurred from 300,000 years after the Big Bang. Yes, we did just skip like half of the universe, but still, it gets worse later in the presentation. So, matter domination occurred from 300,000 years after the Big Bang to 500 years after the Big Bang. I really hope I'm not waving my hands this much tomorrow. So, we actually are kind of unable to observe most of the stage of the universe. Along with everything prior to this. I'm pretty confident about that. Because the cosmic microwave background, CMB, was created around this time, in this time period. Next slide does have more info, I think. Oh, it does. Cool. So, actually, here's an artist's interpretation of the universe at this stage. You can see here's a bit of black. That's what it looked like before the CMB, cosmic microwave background. Ignore that part, though. Next slide. Okay, so cosmic microwave background. It was generated when the universe was approximately 380,000 years old. So here's what our homie universe looks like. This was actually discovered accidentally when scientists were looking through telescopes in the 60s. It's on the next slide. But saw loads of interference with their telescopes in the microwave spectrum because, they were using microwave telescopes. So, yeah. They spent actual ages looking for some sort of interference on Earth but found nothing, and eventually came to the conclusion that it was the light from the creation of the universe. Yeah. Next slide. So, here's a picture of that telescope. It looks really weird. Nothing like a current telescope, but really kind of interesting. I'd like to see it. Okay, so, the first observation of the CMB took place in the 60s using a ground-based telescope shown there. And the second attempt was actually made about 30 years later using a satellite called COBE. COBE. I'm not saying the basketball guy. Is he basketball? I think no. He's no. He is golf. Yes, that guy's golf. Except it starts with a K, right? I don't know. This gave us an actual, much more detailed observation of the CMB than the first observation. And judging on how that looks, you can pretty much guess how bad this one was. It was basically just a blob. And yeah. The third attempt was in 2001, made by a satellite called WMAP. The fourth, that looks a lot better than COBE. The fourth and so far final attempt, named Planck, after Max Planck, I really hope I'm saying that right, was launched in 2009 and provided the most detailed observations so far. There's that one. It's also this one, but still doesn't matter. Cosmic Microwave Background CMB Part 3. So, what is the actual importance of the CMB? Well, it gives us the earliest view of the universe, as I kind of already mentioned hundreds of times. It allows us to view one of the earliest states of the universe, and also allowed observation of the universe when matter was first formed. And for the first 380,000 years, the universe was transparent, and no light had been generated yet. What does that have to do with the CMB? Bugger off. Okay, next. Okay. Formation of first generation stars, Gen 1 stars, whatever you want to call them. They're nothing like the first gen iPhones. Don't know why I wrote it there. My phone just went off. Not right now. We are all stars, albeit recycled ones. Sorry. But the most heavy elements that are on the periodic table were fused by Generation 1 stars. They were propelled in... So they actually, kind of ironic, propelled the universe into 150 million years of darkness. They had very short lifespans. The internet, for some reason, does not know how long they last. I don't know, I spent quite a while looking. And they were made mostly of helium-4 and hydrogen. Yeah. This is actually the oldest star in our stellar neighborhood. It's not actually a Gen 1 star, I don't think, so there's that. Here is the Dark Ages. This is what they looked like. Yeah, basically Dark Ages. Don't really have much on this slide because it's the Dark Ages. Thought it'd be funny to kind of skip it because, you know, Dark Ages, dark slide. Minus the activate Windows button or watermark. Sorry about that. So Dark Ages, the real Dark Ages, occurred from 380,000 years after the Big Bang to 150 million years after the Big Bang. This was way before the first galaxies, stars, and the solar system. Solar systems. Not the solar. Oh, I'm an idiot. Okay. Now, kids kind of tend to whine about how they're in the darkness for like 9 hours in the night. And then, you know, you're like, yo, universe, how do you feel to have been in darkness for 150 million years? And what's it say? You listening? Nothing. I love the universe. Way better than kids. Although it did create kids. But whatever. Technically, it wasn't darkness. We're kind of just unable to view it through telescopes. Sorry about that. And the universe was a big foggy mess of matter. Yeah. So the formation of galaxies and galaxy clusters, that's actually a galaxy merging thing. So there are a few theories on how this happened. Two, right? Yes, there were only two theories on how this happened. The first and least accepted. Nope, I got that backwards. The most accepted one, the bottom-up theory, states that the universe consisted of large clusters of matter pulled them. What? So, the bottom-up theory states that the universe consisted of big clumps of matter whose gravity pulled themselves together, and the Hubble Space Telescope has actually viewed these clumps of matter, which in fact leads us to believe that it's the way it happened. And the previous accepted theory, the top-down theory, it's very unlikely, that it basically states that galaxies are formed by massive clouds of gas collapsing in on themselves. And, you know, they sound very similar, but I assure you they're not the same thing. They are slightly different. There's a very thin line between them. And, yeah. If I went into more detail, there'd be more differences. But still, here is... Okay, so populations of stars may sound weird, may not, I don't know. Population 1, 2, and 3 stars. Those are the populations of stars we know. I don't know what comes after population 1 stars, though. So, can't expect much out of that. I don't think we generally know. What happens? Do we just go population 0, population -1? Don't know. By that time, English probably won't exist, so we'll have to come up with new names. So I'm not too concerned about that. I should stop rambling. Population 3 stars, those are the generation 1 stars. It's confusing, I know. These, as I mentioned previously, contain... crap. So, population 3 stars, mostly consisted... Population 3 stars are actually mostly made up of helium-4 and hydrogen, as I mentioned before. And population 2 stars are... oh my god. This is not a population 1 star, I'd like to point out. So population 2 stars are known as poor metal stars, as they contain lighter metals, and they're mostly made up of helium and hydrogen and contain much larger amounts of metal, because the population 3 stars fused a bunch of metal, and yeah, those went into the population 2 stars. So yeah, now to confuse you even more with population 1 stars. So they're mostly made up of helium and hydrogen, but 1 to 2% of the mass is actually metal, and these did not create the rest of the elements on the periodic table. The population 2 stars did that. Now, confusing you way more, the Sun is an intermediate population 1 star. That basically means it's kind of in between population 2 and population 1. It's closer to population 1, though. So, yeah. Sun is not either. It's kind of both. Blurs the lines. Damn physics. Okay, so I'm skipping 100 trillion years now. Don't ask me why, but this bit of the universe in the 100 trillion years is boring, except for the Elon Musk sending us to Mars and beyond. Birth and death of the Sun, destruction of the Earth, Sun turning into a white dwarf and eventually cooling to the point that light is no longer emitted, becoming a black dwarf, none of which exist in the universe currently. Most other stars dying, the remnants of the solar system orbiting the Milky Way about 435,000 times, and me giving this presentation. So, yeah. Next slide. Okay. So here's a basic chart. Big Bang over here. Here. And the dark matter. Nope. And basically here's a chart of the expansion of the universe over 13.7 billion years. First gen stars, both there, dark ages, basically there. Quantum fluctuations, inflation, I guess. I don't know, afterglow light pattern, basically. Next slide. Okay. So, it may sound weird, and it really is weird, but death of the last star. How many of you did I just lose? Okay, quite a few. So 100 trillion years from now, well, kind of 100 trillion years from now, we're not entirely sure, but about 100 trillion years from now, the last star will burn out, right? And the final star is a red dwarf, and if humanity still exists, first thing you should do is thank Elon Musk, and yeah, this will be the last moments of life. Because that's no longer possible after the star dies. And the universe kind of gets to begin its journey to absolute zero. Yeah. After this, there are still technically last stars, black dwarfs, and the bloody will die and stuff. But that's going to take a little while. Okay, now we get to skip. Wait, we didn't skip. Okay, I'm just making sure. So now we get to skip 100 nonillion years. That is 1 followed by 30 zeros. So quite a few. So there are actually a lot of atoms in a German Shepherd, and a lot of atoms in a 5-pound Chihuahua. But this has more zeros than that. I did start out doing the Earth, but I didn't feel like it because it was way too big. And yeah. Next slide. So, more depressing stuff. Death of matter. Normal matter kind of will cease to exist in 100 nonillion years. And that's not very good. The only matter left in the universe at this point will be black dwarfs, black holes, and neutron stars. So, there's that. Next slide. Okay. So, around the same time, Google, 110 nonillion years to 10 to the 100th power, or Google years after the Big Bang, all matter in the universe will be consumed by black holes or die due to protons due to protons decaying. So rip, I guess. Yeah, rip. Next slide. So Google years after the Big Bang, black holes will die. The eventual yet inevitable death of black holes will be caused by Hawking radiation, and I can basically ensure you that that does not bring back Stephen Hawking, unfortunately. This literally causes black holes to evaporate over time, and if you somehow manage to survive the decay of protons and lived like nonillions of years, you would actually see the occasional flash of light from the evaporation of black holes, Hawking radiation. So that's cool, I guess. Next slide. So now we get to skip Google years. The death of Google search will occur. Well, actually, it's already occurred, but still. So here's the size of that number. Quite a few years. And there's all the atoms in the solar system. So, quite a few. Next slide. So beyond Google years, or a lot of zeros, one and then a lot of zeros, the complete destruction of the universe will occur. The complete and utter destruction of the universe. Let's just make it a bit more dramatic. The complete and utter destruction of the universe will occur. This is summed up by a few theories. 3 main ones, but there are like a lot. So, the most likely is the heat death. Second is the big rip, and third is the big bounce. Don't worry, I'll cover those in the next couple slides. 3, I think. Hopefully 3. Heat death of the universe. The heat death of the universe will be caused by all energy in the universe being completely destroyed. Basically, forget everything science class has ever taught you. So this is most likely to happen, as I mentioned last slide. It's also the most depressing one, in my opinion. And if atoms somehow existed at this point, they will be destroyed because, they're at absolute zero. And absolute zero is a theoretical minimum temperature of the universe, which technically isn't a temperature because the atom wouldn't really exist anymore, and it's not really possible because there's always some form of radiation hitting the atom. But at this point in the universe, it is really possible because there's no more there's no more radiation keeping the atoms warm enough, giving them enough energy to keep spinning, orbiting, shaking, whatever you want to call it. And at this point, new matter will be impossible. I mean, if there were protons, sorry. And the universe will come to a literal standstill. I should put, what's his name? Carl Sagan quote at the end of this. See if there's a good one. So, the big rip. Pretty complicated compared to the last one, as you can see. So, technically, if this is a correct thing, and it is kind of happening currently, atoms and everything are slowly being pulled apart. And, that's fun. So, if correct, this is happening at the exact moment we are speaking, and before that, ever since the Big Bang, basically. And, yeah, I'll get into that. The theory states that galaxies are slowly getting pulled apart, and eventually matter is getting pulled further apart from itself, and that's happening. And this will only occur if the universe is expanding at an exponential rate, unless it isn't, because, if it's expanding on a linear, is that right? Yeah. Okay. If it's expanding at a linear rate or it's decreasing exponentially, next slide will cover the decreasing exponentially, but if it's doing anything other than exponentially growing, it won't really happen. So there's that. So over nonillions of years, that's the biggest number I can think of besides Google, but that's not as fun to say. Multiple things will happen. Galaxy clusters will be pulled apart, and then galaxies will be pulled apart, and then solar systems will be pulled apart, and then stars that once held the solar systems together will be destroyed, and eventually electrons will get so far apart from the nuclei of atoms that even atoms will cease to exist. Pretty depressing. Actually, this is way more depressing than the last one. Actually, it's kind of not, but it's still pretty depressing. So, the biggest bounce, big bounce, is the least depressing, yet also one of the least likely ones. What is that picture supposed to be again? Oh, it's supposed to be a GIF, an animated GIF, but it's not really animated and stuff. That's unfortunate. Will you animate maybe? No? Okay, whatever. Just imagine those getting closer to each other. the things on the outside getting closer to the center one. So this theory states if the universe is expanding at an negative, it's decreasing, the rate of expansion is decreasing. Eventually the universe will slow down to the point that there's so much matter in it that it actually collapses in on itself. And this collapse of the universe will actually lead to the creation of a prior Big Bang, like singularity. So basically Big Bang, but before the bang, which wasn't even an explosion, it was just rapid expansion. So this newly formed singularity will also come along with the destruction of everything. The destruction of everything that remains in the universe. And technically will occur in an infinite amount of times. So, I mean, you're creating a new universe if you do get, like, completely destroyed by the biggest bounce ever. So there's that. And the singularity will actually eventually reach a critical point where it expands into a new universe, which I already said. Okay, so here's a professionally photoshopped version of the Big Bounce because I couldn't find a good picture. So basically we got, that stuff over there, and then it shrinks down into another Big Bang. Thus concludes the universe, and that's unless it bounces back. So, too long didn't read / listen. The universe is about 13.8 billion years old and probably will die forever unless it doesn't. The Big Bang was too complicated to put in a TLDR, and the cosmic microwave background radiation shows us the oldest possible view of the universe, and this entire presentation is theory-based except for the slide where I skipped 109 million years of the universe. So there's that. Yeah. Here's my sources. There's those. There's these ones. Nope, wrong way. Here's these ones. That's supposed to be an image. But my school's web filter wouldn't let me click on it. So, wait, no. It wouldn't let me go to Quora. So I just kind of copied the Google link. So there's that. Here's these. And here's Wikipedia, except for that one NASA link. These actually only provided confirmation on stuff that other articles were saying, and provided a few images, and all images used in this presentation were, what's that called? Creative Commons. So, yeah. That's the slideshow. Holy crap, I've been doing this for 38 minutes. Okay. Thanks for watching this, if you somehow made it to this point of my bad presenting skills. I'm gonna put class through hell tomorrow. Bye.